Up to this point, we've been analyzing vectors from a graphical perspective. So an arrow on a page. The length of the arrow corresponds to the magnitude of the vector, and the direction of the arrow corresponds to the direction of the vector. Okay, but as we've talked about, an arrow is not a vector. It's just a graphical representation. But furthermore, you can absolutely think about vectors with more than 3 dimensions. This is something you'll do a lot in engineering, physics, etc. In particular, if you're talking about a vector that's not to where the parameters aren't directly related to space, like a price vector, cost vector, and whatnot. But even a spatial vector, like a velocity vector, you could have components of X, Y, and Z, but maybe a component of time as well. You look at that as a dimension, for example. And so in that case, when you go past 3 dimensions, we can't really use an arrow to represent a vector. But again, more importantly, though, the big idea is that an arrow is not a vector. So what's the more general, universal way that we represent a vector or a vector quantity? Well, what we do is we use matrix notation. Okay, so a matrix, you're probably at least somewhat familiar with a matrix, is just an array of values arranged within brackets like this. So it's this array of values that has m rows and n columns. Any matrix is going to be like some m by n, have a certain size, m by n. Now, when you have a matrix that contains just one row or just one column, so either m or n is 1, then we call that a vector. Okay, and so that is the general universal way that we represent a vector. So, for example, this would be a vector. 3 minus 1, 2. Or equivalently, you can write this in column form. This is a row vector, but you could write this as a column vector if you want. Okay, and so in this case, since there's 3 values in this row or column matrix, then this is a 3-dimensional vector. Each value corresponds to a dimension. If we had a 2-dimensional vector, we'd have just 2 values. It would be a 1 by 2 matrix or a 2 by 1 matrix. But what you can see is that with this method of representing a vector, we can have any dimension of a vector. We could have a 5-dimensional vector. This is a 5-dimensional vector in column vector form, but you can write it in row vector form. Okay, but how does this represent a vector? Well, to see how this works, we can take a 3-dimensional vector like this or a 2-dimensional vector and construct the corresponding graphical arrow. Because again, we can make a graphical representation of a vector with an arrow in 2 or 3 dimensions. So the general idea is this. So first of all, these numbers here, they're corresponding to distances moved along a coordinate axis of a certain coordinate system. So as this vector sits, this really doesn't mean anything until we specify what coordinate system this vector is associated with, what these values are associated with. Is this 3D rectangular, 3D spherical, cylindrical? Okay, so once that's specified, what these values are corresponding to is distances moved along the first coordinate axis, the second coordinate axis, the third. Okay, however, it's important to note, though, that fundamentally, the coordinates, when you see a vector represented like this, fundamentally, the coordinate system that's being referred to is the vector space of the vector. Okay, so we talked about this in the opening video of this playlist. So if we have some system here, we're in some room or this is a machine, etc., there can be different vectors all over the place. Just like within the same system, you could have different scalars, right? There's weights, temperatures, all in the same system relative to a central coordinate system. Well, vectors are just simple quantities like scalars are, so you can bring in vectors, different vectors. There could be a force vector, a velocity vector, a torque vector, whatever. Okay, but as we talked about, there's the perspective of the coordinate system of the general system itself. Like here we've got this whole machine or this whole room or whatnot. And we put a coordinate system somewhere at an origin. And all of these vectors are located around the origin of this coordinate system. Okay, but there's also the perspective of the vector space of the vectors themselves, in which case the tails of the vectors are always fixed at the origin of the vector space of that vector. It doesn't make sense otherwise for a vector to have its tail not fixed on the origin of its vector space. Okay, like shown here, this gives you a visual indication of the vector space of each vector associated with each vector. This is the vector space of all potential 3D force vectors, but with just one of these potential vectors specified. This is the vector space of, let's say, all potential velocity vectors. And weight's not in here. Okay, this is the vector space of all potential torque vectors, with just one of these torque vectors specified, 3D torque vectors. Okay, and so now the vector space of a vector, when you think about the coordinate axes, what the units of the coordinate axes are in. So, for example, for a general spatial coordinate system, the units of the coordinate axes are going to be something like inches or feet or meters. Okay, but in general, we can put any kind of unit on a coordinate axis. We could put price, or that would be dollars, let's say, or whatever, energy. Okay, and so the units of the coordinate axes of a vector space, for a vector space coordinate system, are going to be the same units as the vector itself. So, okay, this is a force vector. So let's say this is in kilonewtons. Well, this is going to be kilonewtons in the x direction. This is going to be kilonewtons in the y direction. This is going to be kilonewtons in the z direction. This torque here, this will be maybe kilonewton meters. Torque in the x, torque in the y. This is going to be velocity, like meters per second in the x, meters per second in the y. And that's exactly when you have a vector written like this in matrix form, that's exactly what these numbers are corresponding to. It's the component of velocity in the, let's say this is the x direction. This is the component of velocity in the y direction. This is in meters per second or whatever it would be. Feet per second, whatever. Miles per hour. This is in feet per second. This is in feet per second, right? So the main point I'm trying to illustrate here is that when we look at a matrix representation of a vector, we're not thinking about the master coordinate system, where this could, theoretically be any kind of units here. I mean, if we're dealing with spatial vectors, then it's going to be spatial units, but this could be meters. Meters in the x, meters in the y, meters in the z, or whatever, feet. But when you have a bunch of different vectors, I mean, those vectors are going to have their own units associated with the vector quantity. And same with the vector space axes. So it's important to note that when you have a vector matrix like this, we're not referring to, it's not referring to the components along the master coordinate system axes. This is referring to the vector space, components along the vector space coordinate axes. Okay, but still though, how does this correspond to a vector? So this is a 3D vector, so how do we construct this 3D vector within its vector space? Let's say this is the velocity vector space. Okay, well, once again, first of all, this technically doesn't mean anything until we specify what the coordinate system of the vector space is. Here we're showing rectangular vector spaces, rectangular coordinate system vector spaces, but you can have any coordinate system within a vector space that you want. We could have this vector v with a cylindrical coordinate system mapping out the vector space, or rectangular, whatever. So let's say that we're specifying that this vector is defined relative to a rectangular coordinate system. So, okay, here's the vector space of this vector. Let's say this is a velocity vector, and this is the vector space of all three-dimensional velocity vectors. Okay, what that means is that this is, so if this is not x, y, and z. No, this is velocity in the x, velocity in the y, velocity in the z. Every tick mark that we move in this direction is going to be like 1 meter per second in the x direction, 2 meters per second in the x direction. Every tick mark here will be a certain meter per second, whatever, however we have it scaled in the y direction. Okay, and so let's put some tick marks here. Okay, so regardless of the coordinate system in the vector space, we use the exact same process to construct the vector. So we're gonna start at the origin, because any vector within its vector space is going to have its tail fixed at the origin. So we start at the origin, and we think about that as the starting point, the initial point. Then from that point, from the origin, we're going to go 3 units in positive x, 1 unit in positive y, and 2 units in positive z to arrive at a second point. So let's do that. 3 units in positive x. Okay, we're here. 1 unit in negative y. So now we're over here. Okay, now 2 units in positive z. So we're, let's see. Okay, so this is the second point. And we mark this off. So we have the initial point and now the second point after moving along the distances specified by the vector. Okay, and so now next what we do is we just connect the origin to this point and put an arrowhead at the second point. And that is the vector v. That's it. Now you might be thinking, well, isn't it going to be different with a coordinate system that has curved axes, you know, or like angular axes? No, it's the same. It's going to be the same exact idea. You start at the origin, and then it doesn't matter if you have an angular axis or a radial axis. You just move along those axes, and you're going to get to a second point. And then just connect, no matter what the coordinate axis is, just connect the 2 points with a straight line, put an arrowhead at the second point, and that's it. That's the vector. Okay, let's take a look at another coordinate system. So, okay, we've got, let me bring in, so okay, we've got a rectangular coordinate system in the background, and then we'll overlay a cylindrical coordinate system. Okay, now, but if we think about the vector as an actual physical object that isn't aware that a coordinate system is there, then we can think about converting this vector in rectangular coordinates. So let me draw this in real quick. Okay, we can think about the idea of we have this exact same vector, but we've just switched coordinate systems, and we want to represent this vector just with this different coordinate system. So in this case, cylindrical. Well, when you do that, what's going to happen is the component quantities in general are going to change. If you have a different coordinate system, but you're trying to map the same point or the same object, then all the coordinates are going to, the quantities are going to change. If you just leave the quantities the same and plot 3 minus 1, 2 in cylindrical, you're going to get a different vector. So in a cylindrical coordinate system, this is actually a different vector. This would be some other vector p. But what would vector v be in cylindrical? Well, we just need to convert these from rectangular to cylindrical. We talked about the conversion formulas between the 3 main coordinate systems, rectangular, cylindrical, and spherical. Okay, so we know that the z component is the same between rectangular and spherical or cylindrical. Okay, now we know that we can get r using the relation that r is equal to the square root of x squared plus y squared. So in this case, we've got 9 plus 1. 3 squared is 9 minus 1 squared is 1. So r is equal to the square root of 10. Okay, and then we have the relation that tangent of theta is equal to y over x. So theta is equal to arctangent of minus 1 over 3. So let's see. Let's do this in radians. Well, let's start in degrees and then we'll convert it to radians. So arctangent of minus 1/3 is minus 18.4349 degrees, but we know that the inverse tangent function is just going to give you something between minus 90 and 90. But we know that there's going to be two angles between 0 and 360 that are going to give you that to where their tangent is equal to minus 1/3. So we need to analyze our problem here to see what angle we've got. And it looks like it is going to be about minus 18. So this is, we can just go ahead and use this. The other angle would be what? So tangent is negative in the second and fourth quadrants. So you have another angle in the second quadrant, but that's not the angle. So we can write this as theta is equal to this, or we could say, you know, so 360 minus this. So it's 360, well, 360 minus or plus this. So we could say this. So if we could just go ahead and do this in radians, though. Minus 0.322 radians. And there you go. There's vector v in cylindrical. Okay, but let's go ahead and plot vector p with the same numerical values, 3 minus 1, 2, that were used for v in rectangular, but now let's plot these same numerical values in cylindrical. So, okay, so same process. We start at the origin. That's the start point. Then we go 3 units in the r direction, 1, 2, 3. So we're on this circle here. Then we go minus 1 radian in the theta direction. So minus 1 radian, that's about 57 degrees. So, okay, this is 90 degrees, or minus 9 degrees. Here's minus 45. So right around here. Okay, then we go 2 units in the positive z. So let's see. Here's the second tick mark in the z. So I'll draw that parallel to the r there, and then, and so there it is. There is P. Okay, now what about spherical? Let's look at spherical. Okay, so I'll leave the rectangular coordinate system in the background for reference, and there's V, the original V that we plotted in rectangular as 3 minus 1, 2, and then we converted it to cylindrical and plotted it again. Now let's convert it to spherical. So it's not going to be, we're going to have some new vector M in spherical that's going to have the components 3 minus 1, 2. Okay, but what would the vector, so this was vector V in rectangular, right? 1, 2, 3, minus 1, 1, 2. But what would this vector V be in spherical? Okay, well, the conversion formulas that we derived were okay. Well, if you do some manipulation with these equations here, you can solve for rho, theta, and psi. Okay, so let me put in these axes. Here's the theta axis. Here's the psi axis. Okay, so we've got, okay, so, and then there's rho. So you've got psi, theta. Okay, so if you work with these equations here, what you're going to get is, so you have theta is equal to arctangent of y over x. There's one formula. So, okay, we've got y and x, 3 minus 1. And so that's actually, that's the same as what we solved for previously, right? Minus 0.322 radians. So there we go. The second component here is going to be minus 0.322. Theta's, that makes sense. We're right around here. Okay. Now we've also got that rho is equal to the principal square root of x squared plus y squared plus z squared. Okay. So in that case, we've got 9 plus 1 plus 4. So that's, okay, there we go. Okay, now for psi, we've got that psi is equal to arctangent of the square root of x squared plus y squared over z. So, okay, that is, let's see. 3 squared is 9 plus 1 squared 1, so square root of 10 over 2. All right, so that's in radians, so let's see what this is in degrees. 57.7 degrees. Yeah, so 1 radian, about 1 radian. Now, do we need to consider the other angle that satisfies this inverse tangent? Well, that would be in the third quadrant. No. This is going to be 57 degrees or 1 radian because we're going to do this. We're going to go root 14 in the radial direction, any radial direction, but then theta puts us about right here, so we're somewhere here, and then we go, this is about 57 degrees, 1 radian. So that's it. This is going to be 1, positive 1 radian. So there's V in spherical. Okay, but now let's go ahead and plot M. 3 minus 1, 2. So, okay, start at the origin, and now we move along these coordinate axes, these amounts, to get to a second point. So, all right, we start off with 3 spheres away from the origin. So this is our rho is equal to 1, and this is rho is equal to 3. I didn't draw the even spheres. It's hard to see. So we're not here. We're somewhere on this row here. Okay, now theta is equal to minus 1, so that's about minus 57 degrees. So there's about minus 45. There's about minus 57, so right in there. And now we're somewhere on this, you can think about a circular cross-section of the sphere. Rho is equal to 3. So let's see, here. But we're somewhere on this circular cross-section because we're fixed at that theta. We're fixed at this. This is minus 45. This is minus 57. That's about minus 1 radian. So now where are we? Now we go 2 radians in the psi direction. So in general, psi, so 2 radians is going to be, let's see, 2 radians is about 115 degrees. So actually, we're okay there. In general, psi is going to be between 0 and 108 degrees, 0 and pi. But as I've mentioned, it's not like you can't think about plotting any real number with, rho. You can't. Rho is technically, there's no reason for rho to be negative or r to be negative in spherical. But if you had a negative rho or negative r, then all you would do is you would just think about plotting it like normal, but then you'd go the other direction with rho. Like you could still plot, negative values for these coordinates in these systems. You can still think about doing that. But in general, it's redundant to have a negative rho or a negative r or a psi that's less than 0, greater than 180. But in this case, it doesn't matter. So because 2 radians is about 115 degrees. And so that puts us at, let's see, so we're on r's, or rho is equal to 3. So there's 90. There's 135. So right around here. Okay. This is psi. You see, this is theta, and this is psi, and we're fixed on this rho is equal to 3. So that's it. There's the second point. We mark off the second point and connect the origin with that point. And that is the vector M, which is this 3 minus 1, 2 in spherical. Okay, so now, but what about higher dimensional vectors? Like a 7-dimensional vector. How do we interpret this in the context of an arrow on a page or just 7-dimensional space? Well, what we do is we think about higher dimensional coordinate systems abstractly. We abstractly extend any coordinate system to higher than 3-dimensional space. Now, but which coordinate system do we use? Well, there's ways of extending any coordinate system abstractly to higher than 3 dimensions. You could do this with a cylindrical coordinate system, a spherical coordinate system, a rectangular, whatever. However, most commonly, when we have these higher dimensional vectors, we're going to be abstractly extending a rectangular coordinate system to more than 3-dimensional space. And there's 2 reasons why you can think about that we're going to be most commonly using a rectangular coordinate system to do this. The first reason is that, so this is a matrix, right? It's a 7x1 matrix. These vectors are just one-dimensional matrices in the sense that they have either just one row or one column. But they are matrices. And matrices come from linear algebra. That's what linear algebra is all about. It's working with matrices. Well, linear algebra is called linear algebra for a reason. There's different ways you can learn linear algebra, and one way is from the graphical perspective, transformations of spaces. And with linear algebra, what makes it linear is that the coordinate axes are all straight lines. Or if that wasn't the case, it wouldn't be linear algebra. And so with that, since we're dealing with matrices here, that's why it's very common to go ahead and think about this as just an extension of a rectangular coordinate system with straight line axes. Okay, but another reason you can think about is that it's a very simple, intuitive extension when you extend a rectangular coordinate system to more than 3 dimensions. And the reason is because with a rectangular coordinate system, it's all straight line coordinate axes, and they're all perpendicular to one another. So when you go to 4 dimensions, it's like you're just adding a 4th straight line coordinate axis that's just perpendicular to the previous 3. Same idea with a 5th axis, a 8th axis. But with something like a cylindrical coordinate system, for example, well, what's the next axis that you're adding? Is it going to be radial? Is it going to be the angular? Is it going to be the linear? So it gets a little more ambiguous in those cases. But there are methods to where that you can think about extending those kinds of coordinate systems to higher than 3 dimensions. But still, it's a lot simpler with rectangular. But then furthermore, this is a matrix from linear algebra, the straight line coordinate axes. When you do transformations in linear algebra, you start off with a rectangular coordinate system. Okay, now you still might be a little bit confused because if you've watched certain YouTube videos or taken certain courses, So let's say this is some coordinate system within a room, a machine. So an actual coordinate system mapping out a space. Okay, and within that coordinate system, we can bring in different vector quantities and scalar quantities as well. Okay, but you might have seen examples where vectors or vector arrows are constructed off of the origin relative to a coordinate system like this. So what's that about? What's going on there? But then also, you might be wondering, so a vector is contained within its own vector space. You might be wondering, well, is there any relation between the vector's vector space and like the master coordinate system? There should be some relation, right? When it comes to the vector space of a vector, do we not have to consider the coordinate system that we're putting it in at all? Well, okay. To answer these questions, one thing you really want to keep in mind here as we go through this, it's going to be really helpful for you, is that really keep in mind that we're talking about these graphical representations of vectors, these arrows. Okay, we're not talking about actual vectors. We're just talking about what's the best way to graphically represent vectors for our own intuitive way of viewing a system with vectors, or for presenting a system to people. Okay, I would always, when I was first learning vectors early in engineering, I would always have to catch myself. I would be thinking, oh man, I don't understand vectors. Vectors are confusing. Because, where does the tail go? How do you construct the vector here? We're not constructing actual vectors. We're constructing vector arrows. There's no tail of a vector. It would be like if you collected some data from the environment, or from a biological system or machine or whatever. You got all this data, and now you're trying to put it into Excel, put it into some graphing software, and trying to graph it. And the graph isn't lining up like you want, and you're trying to make it work, and you're starting to think that the data itself, I don't understand the biology, the biological system. I don't understand the environment. What do you know that you don't mix the graph with the actual what's going on in physics or biology, right? This is just a way of presenting the data. This isn't the data itself. Okay, now. The next thing we want to think about is that, so we can have a space, right? We can have an actual physical space itself in a room or a machine or the environment, to where the master coordinate system is a spatial coordinate system, X, Y, Z, but like this is in feet. These coordinates are in feet or inches, etc., right? A spatial coordinate system in a factory, whatever. Okay, but we can have abstract spaces. This could be the weight of a package, the volume of a package, and the price to ship the package. This isn't space itself, right? But it's still a space in an abstract sense. Okay? Well, when you bring a vector or even a scalar into a quote-unquote space, you can't just arbitrarily bring any vector into a space. The vector is going to have it's going to have an intimate relation to that space, in the sense that these are spatial vectors here. Well, you're going to be bringing a spatial vector into actual space, into actual, this is in feet, this is in inches. Otherwise, it wouldn't make any sense. It wouldn't make any sense to bring in, if this was weight, this was volume, this was price. It wouldn't make any sense to bring a force vector in here. You could bring a price vector in here, maybe a weight scalar, but a force vector? No. As we talked about, when you have a spatial vector, okay, what makes it a spatial vector is that the underlying definition of the quantity, the force, the velocity, the angular acceleration, etc., the underlying definition, it's going to contain a change in linear distance or a change in angle, both of which have a relation to space itself. So it makes sense that you bring in a force or a velocity or torque into a spatial coordinate system. And same thing with weight or temperature. You can have temperatures in space. Any physical phenomena is actually in space. Okay, so in that sense, there is an intimate relation between the vector space coordinate axes and the spatial coordinate axes that you bring them into. Even though, as we've talked about, this is not x, y, and z. This is force in the x, force in the y, force in the z. This is, you're not moving when you go along this axis, you're not moving a distance, you're moving a certain amount of kilonewtons in the x direction. Here, you're moving a certain amount of meters per second in the x direction. Here, this is a certain amount of rotation about the x-axis or angular acceleration about the x-axis. Okay? And so now, but this is just a graphical representation, so you can technically do whatever you want. It's just a graph. You can present it however you want. Okay? But one rule of thumb that you can think about that you're going to need to do when you're bringing vectors into a space, or else your graph's not going to make sense, is you're going to want to have the directions of the coordinate axes of the vector space lined up with the directions of the main spatial coordinate system, so that the actual vector itself is pointing in the same direction that it corresponds to in the main space. Now, you could technically do this with a vector space coordinate system that's different from the main spatial coordinate system. You can still line up the directions. You could think about lining up the directions. However, that would be pretty confusing as well. So a good rule of thumb is that you're going to want to make the vector space coordinate system match up with the coordinate system that the main coordinate system that you're using, and then you're also going to want to line up the directions. So you're going to want to make, this is going to be the velocity in the x, this is going to be the velocity in the y, this is going to be the velocity in the z. And you're not going to want to do, you don't want to do this. No, that's confusing. Even though you could still, the information is still there, you can still, okay, this is the velocity in the z. So now I got the amount of velocity in the z, so now I need to kind of reconstruct the z direction is here, so I got to put that velocity here. That would just be confusing. So no, you want to line them up. You want to line them up, and you want to make the vector space in the main coordinate system, the type of coordinate systems match. Okay, now, but what about the magnitude of the vector? We know that the magnitude of a graphical vector arrow corresponds to the length of the arrow. Okay, now, but if we think about how, so we can scale this. Let me put in velocity. We have velocity in the x. Okay, we can scale this however we want, and the direction is still gonna be correct in terms of its relation to the main coordinate system. As long as we had it lined up to begin with, then it doesn't matter how we scale it, the direction is going to be correct. Okay, now, but when it comes to the magnitude of the vector, you might say, oh, but no, we're changing the magnitude of the vector when we do this. Well, no, not in relation to the vector space. We're not. No matter what, you can still always come into the vector space. If you're like this, you can still come into the vector space, and if you go velocity in the x and you kind of add all of those together, the velocity in the x, y, and z, and you add all those together to get the magnitude of the vector. We'll talk about how to do that later. You're still going to get the correct velocity based on the vector space coordinate system, no matter how you have this scaled. Okay? The only issue is that if you're looking at the length of this vector relative to the main coordinate system, then it can get kind of confusing. If you're trying to relate the magnitude of this velocity in terms of the length of the arrow to the main coordinate system, well, then that might be a little bit confusing. And the answer to how we would address this is that there is no good answer here, because you're going to, when you bring in these vectors into this graphical representation here, it's going to be best to have the arrows kind of match the objects. You know, if you want to put a force vector here, well, then trying to have some sort of relation between the length of the vector and the main coordinate system is just going to be confusing. So what you could do is you have all the vectors in the right directions. You could maybe put a legend off to the side that tells you, okay, the force vector magnitude is this much. the velocity vector magnitude is this much, etc. But since the coordinate systems of the vector space and the main coordinate space are lined up, you could still think about, okay, well, a certain percentage of the force is of this arrow is in the x direction, a certain percentage is in the y direction, a certain percentage is in the z direction. So you could graphically get a sense of the percent of that force magnitude that you read off in the legend. You could get a sense for, okay, a certain amount of that force is in certain percentages in this direction, that, etc. But as far as, a visual idea of, okay, this force vector is a certain amount longer than the velocity vector, so that means that force is a certain amount larger than the velocity, that's going to be hard to communicate graphically. There's only so much you can do. Okay, now, the last thing to talk about is what about when you see vectors constructed off of the origin of a coordinate system, these vector arrows. So you'll see examples. For example, we have this vector v. Let's say it's 5 minus 2 minus 4. Okay, so one, 2, 3, 4, 5, then minus 2. Okay, then minus 4. So, okay. 1, 2, 3, 4. Okay, so we're at this point here. So we went 1, 2, 3, 4, 5. Then minus 2. And then 1, 2, 3. Then down here. All right, so we connect the start point, and that's vector v. Okay, so, but now the way that this will be taught is that, well, vectors aren't, they don't have to be fixed at the origin, they're tails, so you can put this vector, let me make a copy. You can put this vector wherever you want. So these two vectors here are equivalent. If this is v1 and this is v2, then v1 from a vector standpoint, you could have vectors be equal. v1 is equal to v2. Because why? Because as long as the magnitude and the direction of the vector are the same, then it's the same vector. It doesn't matter where they're located, and that's true. That's definitely true. These are the exact same vector. The magnitude and the direction did not change. You could put a vector wherever you want, just like you could put a scalar quantity wherever you want. And so in that sense, you can construct a vector relative to any coordinate system by, you can just pick a starting point. We could have picked this starting point out here. Okay, and then from that starting point, moved 5 parallel to positive x, 2 parallel to negative y, 4 parallel to negative z, gotten to a second point, connected the dots, and gotten this same vector. We could have started here and then constructed the vector from here. And you get and you get the same vector. So what's that about? I thought we can't have a vector as far as it's relative to its vector space off of the origin. Well, you can't. You can't. That's true. But again, these are just graphical representations. So you can if you had a system, okay, here's a spatial coordinate system, and maybe you want to just graphically construct some vectors. Again, it's just graphical. You want to just construct these vector arrows. You want to get a certain length of arrow relative to this coordinate space, and so you just constructing this arrow in there. You can do that. It's just there's different ways of working with vectors. You can draw position vectors. Like if you're mapping out a location in mountains, let's say, in the mountains. Well, maybe you want to construct an arrow between two landmarks, between like the top of a mountain and a building over here. And so you're constructing a vector like that. So, but then you're going to connect the ends of that vector with the origin. There's different ways you might want to use vector arrows off of a main coordinate system. It just depends. Again, don't get bogged down with thinking that, oh, this doesn't make sense physically. These are just graphical methods. Okay, but the reason why I like to teach that when you're looking at the technical definition of a vector from its vector matrix form like this, I like to teach it that this is within the vector space of the vector, and it can only have its tail at the origin, is because if this is a velocity vector, well, this is going to be a component of velocity in the x direction, in the y, in the z. Okay, and so in that sense, this here, having v2 over here and v1 over here, this makes sense if this is a main spatial coordinate system for these vectors. However, if this was a vector space, okay, if this was a vector space to where this was velocity in the x, velocity in the y, velocity in the z, well, then this wouldn't make any sense, because then this would, okay, what would this velocity in the x be, in the y be, right? If you actually line this up with the spatial coordinate system, what would this be? What would the magnitude of this be? Like you can only, when you, again, this would be 5 meters per second in the x, minus 2 meters per second in the y. It wouldn't make any sense if you have a vector off of the origin within its vector space, when the coordinate axes are in the units of that vector. You see the difference? Yes, you can take a vector relative to a coordinate space, x, y, and z. You can take a vector and put it wherever you want, of course, just like you could do that with a scalar. Okay, and if you have the exact same vector, the same vector, it's the same direction and the same magnitude, but also more than that, the same like units, right? So I could have a momentum vector be in the same magnitude and direction as a torque vector, but that's not the same vector. So it's the same quantity as well. So these are both torque vectors, and they're in the same magnitude, the same direction. Well, then those are the same vector, no matter where they're located. Okay, but that's where they're located relative to the main coordinate system, relative to the vector space itself, where the axes of the vector space here would be in kilonewton meters along the x, kilonewton meters along the y, kilonewton meters along the z. This would be in kilograms meters per second. Well, then no, you can't have them located off the origin. That doesn't make any sense, because when you think about a torque vector in matrix form, like minus 3, 2, 1. Okay, these components would be in kilonewton meters. It's relative to the vector space. And so that's why I like to teach, when you're constructing a vector within its vector space, it's only coming from the origin. That's the only way it makes sense. But if you want to, you have the option of constructing vector arrows, graphical vector arrows with certain lengths relative to a main coordinate system. You can do that if you want, from a graphical perspective.